On April 1st, 2026, 4 human beings left Earth. Not to orbit it, not to circle it at a comfortable altitude where the blue glow of the atmosphere still felt close. They left it behind. They climbed higher, faster, and farther than any living person had ever gone. Punching through the silence of cislunar space aboard a vehicle that gleamed like a polished blade, cutting through absolute darkness. The Orion spacecraft, a capsule forged from over 50 years of engineering, failure, ambition, and reckoning. Its metallic hull catching the raw, unfiltered light of a sun, with no atmosphere to soften it. A white so sharp, it ceases to be a color and becomes a physical force. They did not slow down. On April 6th, they broke a record that had stood for 53 years, a record no human being had tried to break since the terrifying silence of Apollo 13, when 3 men found themselves flung farther from Earth, not by triumph, but by disaster. 400,000 kilometers of void, a distance that erases every border, every nation, every missile silo, every flag planted in soil by anyone who ever claimed the future was theirs. Artemis II shattered that record. 406,771 kilometers from Earth. Let that number settle into your body. That is not a headline. That is not a press release. That is the farthest a human being has ever traveled from the planet that created them. And it happened while Moscow and Beijing were watching. Not with admiration, with calculation, because this mission was never just about the moon. The moon is simply the arena. What Artemis II truly demonstrated in the cold arithmetic of orbital mechanics and geopolitical strategy is that the United States has rebuilt the machine that won the first space race, the machine that planted a flag in regolith and transmitted the image back to a world that held its breath. That machine is running again. And this time, it is running against 2 civilizations that have spent the last 2 decades building their own. Russia and China have a plan, a joint plan, architecture and ambition signed in memorandums and broadcast in the vocabulary of peaceful scientific cooperation. The International Lunar Research Station, a rival architecture, a rival vision for who governs the surface of another world. But on April 11, 2026, the Orion capsule broke through the atmosphere at 40,000 kilometers per hour, the fastest crewed re-entry in history, and splashed into the Pacific Ocean near San Diego. The crew was alive. The systems had worked. The data was confirmed. And in Moscow and in Beijing, the clocks that matter most, the ones counting down to the first crewed lunar landing of the 21st century, started running faster. This is not a story about astronauts. This is a story about power, about the moon as territory, about orbital mechanics as the new geopolitics, about what happens when a civilization reignites an engine that the rest of the world prayed had gone cold. The race is real. It has already begun, and Artemis II just fired the starting gun. There is a particular kind of silence that exists only in engineering. It is the silence of a blueprint that has been revised 400 times. The silence of a weld inspected under ultraviolet light at 3 in the morning by a technician who knows that a fraction of a millimeter, a gap thinner than a human hair, is the difference between a crew that comes home and a crew that doesn't. It is the silence of a rocket standing on a launch pad before ignition, when every calculation made by every engineer who ever touched the project is about to be tested by a universe that doesn't negotiate. The Space Launch System, the rocket that carried Artemis II into the deep black, is that kind of silence made physical. It stands 98 meters tall, nearly the height of a 32-story building. And it does not stand still. It breathes. In the hours before launch, liquid hydrogen at -253 degrees Celsius and liquid oxygen at -183 degrees Celsius are pumped through its core stage in rivers of controlled cold. And the entire structure contracts, groans, and exhales plumes of vapor that drift across the Florida coastline like the breath of something ancient and enormous, waking from a long sleep. When its 4 RS-25 engines ignite, engines that were first designed for the Space Shuttle program, reborn and recertified for a new era, they release 8.8 million pounds of thrust in a single second. Not over a minute, not over a countdown, in 1 second. The ground shakes not just at the launch complex, but for miles in every direction. Birds flush from trees they will not return to for hours. The surface of the nearby lagoon ripples as if struck by a stone dropped from heaven. The sound arrives late because sound is slow, and what you feel first is not noise, it is pressure. A wall of compressed air that moves through your chest like a fist made of atmosphere. This is the machine, and the machine nearly didn't exist. For years, for a decade of budget battles, congressional compromises, contractor disputes, and shifting presidential priorities, the SLS program was mocked. It was called a Senate launch system, a vehicle built not to reach space, but to protect jobs in congressional districts. Its cost overruns were staggering. Its development timeline stretched and stretched until the stretch itself became a kind of institutional joke. Engineers who had built the Saturn V in the 1960s with slide rules and determination watched from retirement as a program with 10 times the budget and 50 times the computing power struggled to close a design review. And yet, the machine flew. Artemis II flew in November 2022, uncrewed, a test flight, a proof of concept. And Artemis II flew crewed in April 2026, carrying Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen farther from Earth than any human beings in the history of the species. What this means, what this truly philosophically means, is that humanity's decision to persist in the face of institutional failure and political indifference was vindicated by orbital mechanics. The universe does not care about budget hearings. Gravity does not attend congressional sessions. The laws of physics rewarded sustained human effort with a trajectory that arced around the moon and returned 4 people safely to the surface of the ocean. There is something almost theological about that. Consider what the Orion spacecraft represents in this context. It is not simply a vehicle. It is a philosophical argument made of aluminum-lithium alloy, carbon fiber composites, and radiation-hardened electronics. It is the argument that human beings belong in deep space, that the biological machine, fragile, soft, dependent on oxygen and warmth and a very specific range of atmospheric pressure, can be wrapped in a shell of engineered intelligence and hurled into an environment that is, by every measure, designed to kill it. The Orion's heat shield is the single largest of its kind ever built for a crewed spacecraft. It is constructed from a material called AV coat, an ablative compound that chars and burns away in a controlled sequence during atmospheric re-entry, carrying the lethal heat of hypersonic friction away from the crew module. When Orion returned from its lunar flyby and slammed into the upper atmosphere at 40,000 kilometers per hour, a speed at which the surrounding air cannot get out of the way fast enough and instead compresses into a plasma sheath reaching temperatures of 2,700 degrees Celsius. That heat shield was the only thing standing between 4 human lives and the thermodynamic reality of physics at scale. 2,700 degrees Celsius. That is hotter than the surface of some stars. That is the temperature at which iron melts, at which glass becomes a liquid, at which the concept of solid matter begins to require renegotiation. And the Orion crew sat on the other side of that boundary, behind a shield that burned so that they would not. Now ask yourself this: how many nations on Earth can build that? The answer is not reassuring if you are sitting in a space agency in Moscow or Beijing and reading the mission telemetry that NASA published in the days after splashdown. Russia, the nation that launched Sputnik, the nation that sent Yuri Gagarin into orbit before the United States had finished arguing about whether it was possible, the nation that built the Mir space station and kept cosmonauts alive in orbit for over a year, while American astronauts were still flying missions measured in weeks. That Russia, the Russia of Korolev, of Energia, of the Proton rocket, does not currently possess a rocket capable of sending a crewed spacecraft to the moon. The Angara A5, Russia's most powerful operational launch vehicle, generates roughly 894 metric tons of thrust at sea level. The SLS Block 1 generates approximately 3,900 metric tons. Russia's capacity is less than a quarter of what the United States launched from Pad 39B in the pre-dawn hours of that April morning. That gap is not a technical footnote. It is a strategic abyss. China is closer. China is, in many ways, more concerning to Western space strategists than Russia, because China is not trying to recover lost capability. China is building new capability from scratch, and it is building it with the methodical, long-horizon patience of a civilization that measures ambition in centuries rather than election cycles. The Long March 9, China's proposed super heavy lift vehicle, the rocket designed to compete with SLS, has been in development for years. Its projected specifications would place it in the same thrust class as the SLS. But projected specifications are not test flights. Paper rockets do not carry human beings around the moon. And as of April 2026, the Long March 9 had not flown. Artemis II had. This is the asymmetry that matters. This is the gap that cannot be papered over with press conferences or state media narratives. When a rocket actually flies, when it actually carries human beings into deep space and returns them alive, it generates something that simulations and wind tunnel tests cannot. Validated data, real-world performance numbers, engineering confidence, the kind of institutional knowledge that lives not in documents, but in the minds of the technicians who watched the telemetry in real time and understood instinctively what the numbers meant. NASA now has that knowledge again, and the Orion spacecraft did not make this journey alone. Attached to the Orion capsule throughout the mission was the European Service Module, a contribution from the European Space Agency and built by Airbus in Bremen, Germany. This detail is not a footnote. It is a strategic declaration, because it means that the architecture of Artemis is inherently multinational. It means that the industrial capacity of Europe, the precision engineering of Germany, the aerospace expertise of France, the navigational systems of the United Kingdom, is now structurally embedded in the American return to the moon. When China and Russia look at Artemis, they are not looking at a single nation's space program. They are looking at an alliance, a coalition of industrial democracies whose combined engineering output, whose collective investment in deep space infrastructure, represents a gravitational field of geopolitical influence that is, in a very literal sense, extending beyond Earth orbit. The Artemis Accords, the framework of agreements that governs participation in the program, had been signed by over 40 nations by the time Artemis II launched. 40 nations, each one a node in a network, each one a supplier, a partner, a stakeholder in the outcome of a program whose ultimate prize is not scientific knowledge, though that is real and significant, but the legal and logistical framework that will govern who does what on the surface of the moon, and under what rules, and with what authority. This is where the architecture of the machine becomes something more than engineering. It becomes law. It becomes territory. It becomes the slow-motion writing of a constitution for a world that humanity has not yet set foot on permanently, but intends to. The moon is not empty. It never was. It contains water ice at its poles, water that can be split by electrolysis into hydrogen and oxygen, which are the components of rocket fuel, which means that the moon is not just a destination, but a refueling station, a waypoint, a strategic node on the logistics chain that leads, eventually, to Mars, to the asteroid belt, to the outer solar system. Whoever controls access to that water, whoever builds the infrastructure that extracts it and processes it and stores it, controls the economics of deep space travel for the next century. That is what the SLS was built to reach. That is what the Orion was built to carry people toward. And that is what Artemis II proved, in the merciless language of demonstrated capability, is within the grasp of one civilization and not yet within the grasp of the others. The machine exists. It flew. It worked. And the silence in the mission control rooms of Roscosmos and the China National Space Administration was not the silence of indifference. It was the silence of engineers looking at performance data that belonged to someone else, running the calculations in their heads and arriving at conclusions they would not put in a report. There is a document, signed in 1967, that was written by people who had never left Earth orbit. It was written in the aftermath of the first shock wave, in the years when Sputnik had already screamed across the night sky, and Gagarin had already laughed in the face of vacuum, and the Apollo program was burning through $20 billion, and the fear that space itself might become a battlefield was no longer science fiction, but a genuinely urgent geopolitical emergency. The Outer Space Treaty, signed by the United States, the Soviet Union, and the United Kingdom, eventually ratified by over 100 nations, and enshrined as the foundational legal architecture governing all human activity beyond Earth. Its most famous clause states that no nation may claim sovereignty over the moon or any other celestial body by declaration of national appropriation. Read that again slowly. No nation may claim the moon. It sounds like wisdom. It sounds like the international community at its most visionary, recognizing, in the cold clarity of the nuclear age, that the extension of territorial nationalism into space would be catastrophic. And in 1967, in the context of two superpowers pointing warheads at each other across an iron curtain, it was wisdom. It was the only sane response to a situation in which the flag and the missile were evolving at the same speed. But the Outer Space Treaty was written for a world that did not yet know about the water. In 2009, instruments aboard the Lunar Reconnaissance Orbiter and the L-Cross Impactor confirmed what decades of orbital observation had suggested. The permanently shadowed craters at the moon's south pole contain water ice. Not traces, not molecular hints detected in spectroscopic data that required careful interpretation. Water, billions of tons of it, locked in darkness so absolute and so cold. Temperatures at the crater floors dip below -240 degrees Celsius, making them among the coldest places in the entire solar system. That it has been sitting there, undisturbed, for billions of years. billions of years. The water in those craters is older than the oceans of Earth. It arrived there carried on the backs of comets and asteroids during the period of late, heavy bombardment, when the inner solar system was a gallery of collisions, and it sank into the permanent shadow of polar craters and froze and stayed frozen while single-celled organisms evolved into fish, and fish climbed onto land, and primates descended from trees, and one particular primate built a rocket and pointed it at the sky. That water is now the most strategically important substance in the solar system. Not because you can drink it, not because the scientific value of ancient cometary ice is immeasurable, though it is, but because water, H2O, is 2 hydrogen atoms and 1 oxygen atom. And when you run an electrical current through it in the right conditions, it splits. Hydrogen and oxygen separate, and hydrogen and oxygen, cooled to cryogenic temperatures and stored under pressure, are the propellants that power the most efficient rocket engines ever built. The Moon's south pole is a gas station. It is a refueling depot sitting at the edge of the Earth-Moon gravity well, positioned at the precise location where a spacecraft climbing out of Earth's gravity field can stop, refuel, and then continue to Mars, to the asteroid belt, to Jupiter's moons, to the outer solar system, without having to carry all of that propellant mass up from the bottom of Earth's deep gravity well, which is the single greatest obstacle to affordable deep space travel. Every kilogram of propellant that you do not have to launch from Earth is a kilogram that can be replaced with payload, with science instruments, with food, with radiation shielding, with the infrastructure of a permanent presence beyond our planet. The economics of deep space exploration change completely, not incrementally, but categorically. The moment you can manufacture propellant on the Moon rather than carry it from Earth. This is what the Artemis program is really about. The moon landings that NASA is planning. Artemis II, the first crewed landing, targeting the South Polar region, are not about planting flags for the cameras. They are about establishing a foothold at the most valuable piece of real estate in the inner solar system. They are about putting human beings and their tools within reach of those shadowed craters. They are about beginning the process of characterizing, accessing, and eventually extracting a resource that will determine the pace and scale of humanity's expansion into space for the next 2 centuries. And this is where the Outer Space Treaty, that elegant document written by people who had never left Earth orbit, begins to fracture along lines its authors could not have anticipated. The treaty says no nation can claim the Moon. But it says nothing about resources extracted from the Moon. It says nothing about the right to mine, to drill, to process, to transport. The legal question of whether water ice scooped from a permanently shadowed crater at the lunar South Pole belongs to the nation whose robots scooped it, or to humanity collectively, or to no one, has no settled answer in international law. It is a question that lawyers and diplomats are still arguing about in conference rooms in Vienna and Geneva and Washington, while engineers in Houston and Shenzhen and Moscow are designing the machines that will make the argument moot by the time the law catches up. The United States recognized this vacuum and moved to fill it. In 2020, the Trump administration issued the Artemis Accords, a bilateral and multilateral framework of agreements between the United States and partner nations, governing behavior on the Moon and in deep space. The Accords establish principles of transparency, interoperability, the release of scientific data, and, critically, the right of signatory nations to extract and utilize space resources for their missions, not to own the Moon, but to use what they find there. It is a distinction that sounds technical. It is not technical. It is the difference between a legal framework that enables a permanent human presence on the moon, and one that prevents it. And it is a distinction that Russia and China rejected immediately, loudly, and with a clarity that revealed exactly how high the stakes are. Russia called the Artemis Accords an attempt to impose American legal norms on space. China said they were designed to exclude rivals and establish unilateral control over lunar resources under the cover of multilateral language. Both nations were correct that the accords were designed to shape the legal environment in ways favorable to the United States and its allies. They were also both correct that the alternative, the absence of any governing framework, would be worse. But correctness was not the point. The point was positioning. The point was the opening move in a legal and diplomatic competition that will play out over decades and whose outcome will be as consequential as the treaties that carved up Antarctica, or the conventions that governed navigation of the high seas, or the agreements that determined who owned the electromagnetic spectrum. The point was, whose rules will govern the moon? Russia and China responded with their own architecture. The International Lunar Research Station, the ILRS, is a joint Russian-Chinese proposal for a permanent robotic and eventually crewed base at the lunar South Pole. Developed under a framework that explicitly positions itself as an alternative to Artemis. It invites other nations to join, not under American-shaped rules, but under a different set of principles. Ones that emphasize common heritage, collective governance, and an explicit rejection of the resource utilization framework that the Artemis Accords establish. On paper, it is a scientific program. In practice, it is a counter-coalition. And here is where geography, the oldest force in geopolitics, the one that preceded diplomacy and law and ideology by billions of years, reasserts itself with a cruelty that no treaty can soften. The lunar South Pole is not large. The permanently shadowed regions, the crater floors where water ice exists in quantities sufficient for industrial extraction, cover a finite area. The craters themselves have names now: Shackleton, Hayworth, Noble, de Gerlach, circular wounds in the moon's ancient surface, ranging from a few kilometers to over 70 kilometers in diameter, their floors never touched by sunlight since the moon settled into its current axial orientation billions of years ago. Their rims, by contrast, receive near-continuous solar illumination, making them ideal sites for solar power generation. Crater rim plus shadowed floor equals energy source plus water source equals the complete package for a self-sustaining outpost. There are only so many such locations. And the moon, unlike Earth, has no mechanism for resolving competing claims through the slow pressure of time and negotiation. There is no weather to erode contested boundaries. There is no population to displace or assimilate. There is only the surface, the ice, the solar panels. And whoever got there first and built something permanent enough that moving them becomes more costly than accommodating them. This is why the race to the South Pole is not metaphorical. It is not a race in the way that sporting events are races. Competitions governed by rules, judged by neutral parties, resolved in a defined time frame. It is a race in the way that the settlement of continents was a race, in the way that the laying of the transcontinental telegraph cables was a race, in the way that every moment in human history, when a transformative technology intersected with a scarce resource and an absence of law, produced an outcome that determined the distribution of power for generations afterward. The moon is about to be that moment. And Artemis II did not just prove that the United States can reach the moon. It proved that the United States can reach the moon with human beings, with a sustainable architecture, with allied industrial partners embedded in the mission structure, and with the political will to follow through on a program that survived 2 presidential administrations and a decade of skepticism. That proof is not symbolic. Proof in aerospace is a technical term. It means that the system has been tested under real conditions and has performed within its design parameters. Proof means the data is real. Proof means you can build the next mission on the foundation of the last one without starting from assumptions. Proof means that the gap between where you are and where you need to be is now measurable rather than theoretical. For the Artemis program, Artemis II is proof. For Russia and China, Artemis II is a clock. Not a clock counting down to a launch, a clock counting down to a moment. Perhaps 5 years from now, perhaps 8, perhaps 10. When a human being in a white pressure suit will step off a ladder and onto the floor of a permanently shadowed crater, reach down and scoop a handful of ice that has been sitting in that darkness for 4 billion years. And whoever holds that handful of ice will not just be holding a scientific sample, they will be holding the first brick of an economy that does not yet have a name. The question that Moscow and Beijing are asking, the question that their strategists and engineers and policymakers are turning over in the silence of their respective mission control facilities, is not whether that moment will happen. It is whether they will be there when it does. And after what Artemis II demonstrated in the cold mathematics of demonstrated orbital capability, that question has become significantly harder to answer with confidence. The ground has shifted, not the ground beneath their feet. The ground beneath the moon. There is a launch pad in Kazakhstan that the wind has been slowly consuming for 30 years. It sits at the Baikonur Cosmodrome, the oldest and largest space launch facility on Earth. The place where Sputnik left the ground, where Gagarin strapped himself into a capsule smaller than a modern bathroom, and became the first human being to see the curvature of the planet from above. The pad is called Site 110, and it was built to launch the N-1 rocket. The Soviet answer to the Saturn V, the machine that was supposed to carry Soviet cosmonauts to the moon before the Americans could get there. The N-1 never made it off the ground successfully. Not once. It flew 4 times between 1969 and 1972. Every single flight ended in catastrophic failure. The second launch, in July 1969, days before Apollo 11 landed on the Sea of Tranquility, produced the largest non-nuclear explosion in human history. Up to that point, when its 30 NK-15 engines, burning simultaneously in a configuration so complex that no computer of the era could model it reliably, destabilized, and the rocket fell back onto its own launch pad. The explosion was visible from space. It destroyed the pad, damaged surrounding infrastructure, and set back the Soviet lunar program by years it did not have. Apollo 11 landed on the moon 3 weeks later. The Soviets never admitted they were trying to reach the moon first. For decades, the existence of the N-1 program was classified. The failures were buried under state silence so complete that Western intelligence agencies spent years debating whether the Soviet lunar program was real or an elaborate deception. It was real. It was desperate. And it failed not because Soviet engineers lacked brilliance, they did not, but because the program was starved of the one resource that the Apollo program had in abundance: centralized, sustained, politically protected funding channeled through a single coherent management structure. The Apollo program had a singular architect in Wernher von Braun, and a singular political mandate delivered by a president who had stood before Congress and committed the full weight of the American state to the task. The Soviet program had Sergei Korolev, a genius of comparable magnitude, a man who had survived Stalin's gulags and returned to design the most consequential rockets of the 20th century. But it also had institutional fragmentation, competing design bureaus that hoarded resources and information from each other, and a political culture that could not tolerate the public acknowledgement of failure. Korolev died in 1966 during a routine surgery, and with him died the singular vision that might have held the program together. The N-1 was his successor's compromise. A rocket assembled from the competing demands of institutions that would not cooperate. Powered by 30 engines, because no single engine powerful enough for the task could be agreed upon and built in time. 30 engines. The Saturn V used 5. That number, 30 versus 5, is not just an engineering data point. It is a symptom. It is the technical expression of a political pathology. Every additional engine is an additional failure point. Every additional failure point requires additional monitoring systems, additional redundancy, additional inter-engine communication. The complexity grows not linearly, but exponentially. And at some threshold of complexity, the system becomes impossible to control with the computational tools available. The N-1 crossed that threshold, and the universe responded, as it always does, without malice and without mercy. But here is what history tends to obscure in its focus on the drama of those 4 explosions. The Soviet Union did not lose the space race because it was less capable than the United States. It lost the space race in part because of how it was organized, and in part because of what happened afterward. What happened afterward was the dissolution of the state that built the rockets. In 1991, the Soviet Union collapsed. And when it collapsed, it took with it the institutional infrastructure, the supply chains, the classified knowledge networks, the culture of engineering ambition, and, most critically, the budget lines that had sustained one of the most sophisticated space programs in human history. Overnight, the engineers who had designed the Proton rocket, the Soyuz capsule, the Mir space station, found themselves working for agencies that could no longer pay reliable salaries in a currency that retained its value. Some of them left for other industries. Some of them left for other countries. Some of them stayed and did what they could with what remained. And what remained was considerable, but diminishing. Roscosmos, the Russian state space corporation that emerged from the wreckage of the Soviet space program, inherited extraordinary legacy infrastructure and extraordinary legacy expertise. The Soyuz rocket, derived from the R-7 missile that launched Sputnik, continued to fly with a reliability record that is genuinely remarkable. For a decade after the Space Shuttle Columbia disaster, Soyuz was the only vehicle capable of carrying human beings to the International Space Station. Russian cosmonauts kept the station alive. Russian propulsion technology, the RD-180 engine, powered American Atlas V rockets for years, an irony so complete that it bordered on the philosophical. But legacy is not a growth strategy. Legacy is what you live on while you figure out what comes next. And Russia, for 30 years, did not figure out what came next. The Angara rocket, Russia's next-generation launch vehicle designed to replace the aging Proton, entered development in the 1990s. Its first successful launch of the heavy-lift Angara A5 variant did not occur until 2020. Nearly 30 years from conception to demonstrated heavy-lift capability. During those same 30 years, the United States developed and flew the space shuttle through its full operational life. Retired it, developed and flew the Falcon 9, developed and flew the Falcon Heavy, and developed and flew the Space Launch System. SpaceX alone, a private company that did not exist when Angara entered development, built and flew a rocket more powerful than anything in the Russian inventory. The gap did not open slowly. It opened like a fault line, invisibly for years, and then, all at once. And then came Luna 25. In August 2023, Russia launched its first moon mission in 47 years, Luna 25. A robotic lander designed to touch down near the lunar south pole to demonstrate that Russia could still reach the moon, to reassert the legacy of a program that had once led the world. The mission was freighted with national symbolism so heavy that the engineering itself seemed almost secondary. This was Russia saying, "We are still here. We are still a space power." The South Pole belongs in our story too. Luna 25 crashed on August 19, 2023. The spacecraft entered an incorrect orbit during pre-landing maneuvers. An engine burn lasted longer than commanded. Longer by a few seconds, a deviation so small in human time that a person blinking might miss it, a deviation so enormous in orbital mechanics that it changed the trajectory from a landing approach into a collision course. Luna 25 struck the lunar surface at a velocity that left nothing intact. There was no data from the surface. There were no images of the South Pole. There was only the silence of a spacecraft that had crossed 384,000 kilometers of space and then ceased to exist 4 seconds before it was supposed to land. India's Chandrayaan-3 landed successfully 3 days later, in the same target region, with a rover transmitting data, alive. The juxtaposition was merciless, not because India's success diminished Russian engineering. It did not, because the two missions were designed independently, and their outcomes were independent. But because the juxtaposition was visible, global, transmitted in real time to every space agency on Earth, to every journalist covering the new space race, to every diplomat and strategist who watches capability demonstrations the way an earlier generation watched missile tests. Russia had aimed for the moon and missed. India had aimed for the moon and landed. And 3 years later, 4 American astronauts flew farther from Earth than any human being in 53 years, looped around the moon, and came home alive. Consider what this sequence means to a Russian aerospace engineer who grew up on the legacy of Korolev and Gagarin and the Mir space station, who was trained in a tradition that genuinely believed, with justification for a time, that Soviet and then Russian space technology was among the finest ever developed by any civilization, who watched the budget lines shrink after 1991, watched colleagues leave, watched the Angara program stretch across decades, watched Luna 25 transmitted its last signal at 380,000 kilometers and then went silent. Consider what it means to carry that professional identity into a world where the nation that your country spent the Cold War racing has just demonstrated crewed deep space capability, while your agency is still working on a rocket whose heavy-lift variant first flew commercially in 2024. It means something that does not fit neatly into a press release. It means the ghost of the Soviet program is not a ghost at all. It is a weight, a gravitational presence made of institutional memory and national pride and the cold awareness that the distance between what Russia was in space and what Russia is in space is not closing. It is, in several measurable ways, still growing. There is a specific kind of loss that is harder to bear than ordinary failure. It is the loss of something you once possessed, the loss of a status, a capability, a position that was real and earned and then, through a combination of forces, political, economic, institutional, was allowed to erode until the erosion became irreversible on any timeline that a living person can reasonably expect to see reversed. Russia did not just fail to reach the moon in 2023. Russia demonstrated, in the most public and technically unambiguous way possible, that the infrastructure and institutional coherence required to land softly on another world, a capability the Soviet Union possessed in the 1960s and 1970s, a capability demonstrated by Luna 9's historic soft landing in 1966, had atrophied beyond the point of reliable execution. And yet the ambition remains. This is perhaps the most philosophically complex dimension of Russia's position in the new space race. The ambition is real. The pride is real. The engineers are real. Talented, trained, committed to the work. The ILRS partnership with China is real and represents a genuine attempt to build a new architecture from the foundations that remain. Russia brings to that partnership its deep experience with life support systems, its long-duration spaceflight expertise, its legacy of polar operations on Earth that translates into relevant engineering knowledge for polar operations on the Moon. But experience is not current capability. Legacy is not present performance. And China, Russia's partner in the ILRS, the nation that has positioned itself as the rising counterweight to American space power, knows this. China knows that it is the senior technical partner in the ILRS arrangement, even if the diplomatic language distributes the relationship as one of equals. China knows that its Long March rocket family, its Tianwen planetary missions, its Chang'e lunar program, which successfully returned samples from the far side of the Moon in 2024 with the Chang'e 6 mission, represent a trajectory that is ascending, while Russia's is, at best, stabilizing. The partnership between Russia and China in space is, beneath the diplomatic surface, a relationship between a declining capability and a rising one. Between a ghost and the future it is trying to inhabit, and the future that both of them are trying to reach. The lunar South Pole, the water ice, the refueling infrastructure, the permanent presence, is the same future that 4 American astronauts brought measurably closer when they flew around the Moon in April 2026 and came home to the Pacific Ocean and the validation of every engineer who had spent a decade building the machine that carried them. The ghost of the Soviet program watches all of this from Site 1 and 10 at Baikonur, where the wind continues its work and the concrete of the N1 launch pad continues its slow return to the step from which it was built. Some structures, once broken, do not rebuild. The question that hangs over every strategic calculation in Moscow's space establishment is whether the structure of Russian space power is one of them. Whether the break that began in 1991 and deepened through Luna 25 is a temporary discontinuity or a permanent realignment. Whether the engineers currently designing Russia's next generation of lunar vehicles will live to see them fly successfully. Whether the ILRS will be built on a timeline that matters. In a world where Artemis II is already in development, and the South Pole of the Moon is no longer an abstract destination, but a mission with a crew and a landing system and a schedule. The Saturn V stood 91 meters tall and flew 12 times and put 12 human beings on the Moon. Then America decided it had won and stopped flying it, and 30 years passed and the institutional knowledge dispersed, and it took another 30 years and $100 billion to build something that could do it again. That is what stopping costs. Russia stopped for 30 years. The cost is visible from orbit. There is a philosophy embedded in the Chinese language that has no precise equivalent in English. It is expressed in a single word, Baisheng, which translates roughly as the 100 surnames, a poetic term for the common people, the civilization in its totality, the sum of all the individual lives that constitute a nation across time. It implies a relationship with history that is fundamentally different from the one embedded in Western political culture, where Western democracies measure ambition in 4-year election cycles and quarterly earnings reports. the civilization that gave the world the compass, paper, gunpowder, and the printing press, centuries before Europe had rediscovered the works of ancient Greece, has always understood that the projects worth doing are the ones that outlast the people who begin them. The Chinese space program is that kind of project. It does not move with the urgency of a political deadline. It moves with the patience of a geological force, slow enough that in any given year it is easy to underestimate, fast enough that over a decade it produces results that redefine the competitive landscape entirely. And the results it has produced over the last decade are not incremental. They are not the steady accumulation of small improvements along a known curve. They are qualitative leaps. Moments when China did something that had never been done before by anyone, and did it quietly, without the theatrical countdown broadcasts and celebrity astronaut culture that characterizes Western space programs, and let the data speak for itself. Let the data speak. In January 2019, China landed the Chang'e 4 spacecraft on the far side of the moon. This had never been done before in the history of spaceflight. The far side of the moon, the hemisphere that permanently faces away from Earth due to tidal locking, cannot communicate directly with Earth. There is no line of sight. Radio signals cannot curve around a spherical body. To land there, China first placed a relay satellite, Queqiao, the Magpie Bridge, named for a constellation in Chinese mythology, at a gravitationally stable point beyond the moon where it could maintain contact with both Earth and the lunar far side simultaneously. Then it landed. The Yutu-2 rover deployed, trundled across the floor of the von Karman crater, a basin 4 kilometers deep and nearly 2,000 kilometers in diameter, the largest confirmed impact crater in the solar system, and began returning data. The largest confirmed impact crater in the solar system, and China put a rover in it. On the first attempt, in December 2020, Chang'e 5 landed on the near side of the moon, drilled into the regolith, collected 73 kilograms of lunar material, sealed it in an ascent vehicle, launched that vehicle off the lunar surface, rendezvoused with an orbiting spacecraft in lunar orbit, a maneuver of extraordinary precision that had not been performed since the Soviet Luna program in the 1970s, transferred the samples, and returned them to Earth. The mission demonstrated 4 distinct capabilities in a single flight: precision landing, surface sample collection, lunar ascent, and orbital rendezvous at the moon. Each one of those is a capability required for a crewed lunar landing and return. China demonstrated all 4 simultaneously, robotically, on a timeline that NASA's own analysts described in declassified assessment documents as faster than expected. And then, in June 2024, Chang'e 6 went further. It landed in the South Pole Aitken Basin on the lunar far side, the same vast, ancient impact structure where Yutu-2 had roved 5 years earlier, and retrieved samples from a location no spacecraft had ever reached before. It returned those samples to Earth in July 2024. Rocks and soil from the most ancient, most geologically pristine region of the moon. Material that predates the formation of Earth's continents, that carries within its mineral structure the chemical signature of the early solar system, that will take decades of laboratory analysis to fully interpret. China now has samples from the lunar far side. No other nation has samples from the lunar far side. No other nation has ever landed on the lunar far side. These are not minor achievements in a secondary theater of the space race. The lunar far side is scientifically extraordinary, precisely because it is shielded from Earth's radio noise by the bulk of the moon itself. making it the ideal location for radio telescopes that could observe the universe at frequencies impossible to detect from Earth's radio-polluted surface. It is geologically distinct from the near side, offering a record of the Moon's earliest history that the near side's younger volcanic plains have partially obscured. And it is, in terms of demonstrated landing and operations capability, a place that China has now visited twice, while everyone else has visited 0 times. The philosophy of the long game, expressed in craters. But craters are not the end game. The end game is the South Pole. The end game is the water ice. The end game is the presence, permanent, crude, functional, and backed by the logistical infrastructure that transforms a foothold into a foundation. And China has been explicit about this in a way that space agencies rarely are. Because explicit statements create accountability. And accountability creates pressure. And pressure can be politically inconvenient when timelines slip. China has been explicit anyway. The China National Space Administration and the China Manned Space Agency have both publicly stated the goal of landing Chinese taikonauts on the Moon before 2030. Not eventually. Not in a future administration's budget cycle. Before 2030. That is a hard deadline stated by an authoritarian government with the industrial capacity, the centralized funding authority, and the demonstrated technical trajectory to mean it. 4 years. Consider what China's space program looked like 4 years before Chang'e 4 landed on the far side of the Moon. In 2015, China's deep space capability was real, but unproven at the lunar landing level. 4 years of focused development produced a world-first soft landing on the lunar far side. 4 years before Chang'e 6 returned far side samples, China had not yet demonstrated lunar sample return at all. 4 years of focused development produced the first far side sample return in history. The pattern is consistent. The trajectory is ascending. The 4 years between now and 2030 are not empty time. They are filled with the Long March 10, China's crewed lunar launch vehicle, which is in active development. They are filled with the Mengzhou crewed spacecraft, designed to carry taikonauts to lunar orbit. They are filled with the Lanyu lunar lander, whose name translates as embracing the moon, a piece of nomenclature that functions simultaneously as poetry and as strategic declaration. The Long March 10 is not the Long March 9, the super heavy lift vehicle designed for maximum payload to deep space. The Long March 10 is optimized specifically for the crewed lunar mission profile. It has a projected payload capacity to trans-lunar injection that places it in the competitive range of the SLS Block 1. It has not yet flown. But the Long March family, the Long March 2, 3, 4, 5, 7, 8, 11, has accumulated hundreds of launches across decades, building the institutional knowledge and manufacturing infrastructure that makes each new variant a refinement rather than a reinvention. China does not start from scratch. China iterates. And iteration, in aerospace, is the most powerful methodology there is. It is what transformed SpaceX from a startup that lost its first 3 Falcon 1 launches to a company that routinely lands orbital-class boosters on drone ships in the middle of the ocean and reflies them weeks later. It is what allowed the RS-25 engines on the SLS to be derivatives of engines that first flew on the space shuttle in 1981. Iteration accumulates knowledge in the metal and in the minds of the people who work with it. And that accumulated knowledge is the true competitive advantage in aerospace. More than budget, more than political will, more than any individual technology. China has been iterating for 30 years. The Shenzhou crewed spacecraft first flew in 1999, uncrewed, a test flight. By 2003, Yang Liwei became the first Chinese citizen in space, launched on Shenzhou 5, making China only the third nation in history to achieve independent human spaceflight. By 2022, the Tiangong Space Station, China's own modular orbital facility, built after China was excluded from the International Space Station program by United States legislation that prohibited NASA from bilateral cooperation with the Chinese space program, was complete and permanently crewed. China was excluded from the international community's premier space collaboration and responded by building its own space station. Think about the psychological dimension of that sequence. You are told you cannot come to the table, so you build your own table. You furnish it. You invite your own guests. And then you sit down and demonstrate that the table you built is functional, permanent, and increasingly attractive to nations that the Western Space Alliance has not prioritized. Ethiopia, Pakistan, Venezuela, Egypt, nations that the Artemis Accords framework has not yet fully engaged, have expressed interest in cooperation with China's space program and the ILRS. The counter-coalition is being assembled not through military pressure or economic coercion, but through the soft power of inclusion, by offering a seat at a table that the dominant framework had not set for them. This is the geopolitical dimension of China's space program that pure engineering analysis misses. The moon is not just a scientific destination and a resource extraction opportunity. It is a symbol, and in a world where a significant portion of humanity lives in nations that have complex and often painful historical relationships with Western power, where the narrative of Western technological superiority has been used, explicitly and implicitly, to justify political and economic arrangements that benefited the West at others' expense. China's presence on the moon, China's flag in the regolith of the South Pole, would carry a symbolic weight that no press release from NASA could neutralize. It would say, "We did this, independently, without your framework, without your rules, by our own science, our own engineering, our own patience, our own civilization's relationship with the long arc of history." That is why the timetable matters so much. That is why the race to 2030 is not simply about who gets the water ice first, though that matters enormously. It is about which image reaches the screens of 8 billion people first. An American astronaut standing at the lunar South Pole under the flag of a 40-nation coalition built around American legal frameworks. Or a Chinese taikonaut standing at the lunar South Pole under a red flag that represents the fastest-growing space program of the 21st century and the civilizational ambition of 1.4 billion people. Images are not data, but images shape the contexts in which data is interpreted. And Artemis II produced an image. 4 human beings returning from the farthest point any person had reached in 53 years, capsuled trailing parachutes over the Pacific, recovery crews in orange suits moving across the water toward a spacecraft that had touched the neighborhood of the moon, and come home. That was read very differently in Houston than it was in Beijing. In Houston, it was validation. It was the proof that the machine works.